Good afternoon, everyone, and welcome to the project show of the team GrowbotHub from EPFL Switzerland. They have prepared a video to explain their project and their vision. And after the video, they will have some time to answer your questions. So please use our YouTube chat to submit your questions and comments. Thank you very much for joining us. And now I'm happy to give the word to Victoria.
Hello, my name is Victoria. I'm the team leader of the GrowbotHub project, and I'm here with two of my students lead. We are going to present you two different systems today. One we call the carousel system. It's one to grow leaf vegetables that we already presented last year. And another one is meant to grow root vegetables such as potatoes, carrots, and we focus on growing potatoes this year. Throughout the year, we put the accent on aeroponics and also developing our top-level controller, as you will see in the video that will start in a few moments. As you can guess, we had a lot of problems with the COVID-19, access to a workshop, manufacturing, and also for ordering components. However, we were able to work on a few parts of the systems and build a few prototypes, and we will present to them soon. During the video, you can follow, we will add information about that on the YouTube chat, but there will be some quiz in Instagram where you can win vegetables. I also want to take just a few moments to thank the students who participated in this project, the sponsors, and all the teachers and supervisors that have helped us throughout the year. We'll see you in a moment, and I hope you enjoy the video. Thank you.
Hi, my name is Victoria. I'm the team leader and system engineer for the GrowbotHub project. Our project aims at a fully automated and autonomous system to grow vegetables on the moon. That can seem kind of crazy, and really to make it, our goal is to make it completely automated and completely autonomous. In order to do that, we need a lot of different systems and subsystems. We are here in my living room with a GrowbotHub system. And I just wanted to show a little bit what we are working on before we go into the details. These kind of systems are especially interesting for space. First, because they are long-lasting, as we will see soon, and also because being in contact with vegetables and something living can really improve the state of the astronauts compared to being only in contact with machinery. Also, something, as we will see, we are growing kind of tasty vegetables like peppers and basil, and that can also really help the astronauts as you lose a lot of taste when you go in space. All of these seems really nice, like you can win a lot of space and win a lot of water. And as you know, on Earth, freshwater withdrawal and the size of the lands that are used for agriculture are beginning to be quite problematic. So all of these out-of-soil cultures could be really interesting to reduce ecological impact of agriculture. However, there appear to be some problems with mineral resources depletion, and that is why we are carrying a lot of life cycle assessments on the system in order to determine if it's really sustainable or not. And hopefully we'll be able to publish some information about that by next year. We also want our system to be lasting and user-friendly. That means that all the sensible parts should be accessible to the user, and also the water tank that are placed inside each aeroponic module can only contain enough water to last 5 to 6 weeks. In order to make the system really long-lasting over couple of months, which will be required when we go settle on the moon or Mars, we had to design an external water distribution system where the user can just add the water when some water was extracted, for example, from the soil, and when the nutrients were produced from the bioreactor. So first, we are going to go and discover that water distribution system.
Elliot and I joined GrowbotHub for our bachelor project. We're both studying mechanical engineering at EPFL. We had to design an autonomous system that provides nutrients and water to the 8 sub-tanks. It was a great experience to work in this friendly and well-organized association for both of us. We had to be creative and to use our scientific knowledge in a more practical way to create our system.
Here we can see our final prototype. The two pumps and solenoid valves associated with each subtanks can be activated and deactivated depending on the need in water and nutrients of each plant. Now the prototype will be tested and implemented on the full system, and the next step is to duplicate this prototype for the 8 subtanks.
Okay, we've seen how to bring water and nutrients inside all the different subtanks, and now we're going to see how to grow vegetables on the moon.
So thanks to our robot, the goal is to reach the 20% of daily food intake for the astronaut with fresh vegetables. Thanks to those growing vegetables in those aeroponic system, we can also give to the astronaut the possibility to see other type of life than human ones, which might give some cheerfulness to the astronauts. To reach this goal with our vegetable, we chose 8 different species to grow that all have some nice particularities. The first criteria was to limit maximum the waste by growing vegetables that we can almost entirely eat. Then the second criteria was to avoid maximum the need to cook as it is restrained in space. Finally, we tried to find some with huge amount of kilocalories to fulfill our goal. That is why we ended up with different sorts of salads, such as lettuces, spinach, and rucola that grows fast and easily in an aeroponic system, as well as radish. In order to add taste to their dish, we chose to grow pepper and basil as well. Finally, we added strawberries, as it is a nice fruit, and once it is big enough, it produces strawberry without having to start from a seed again. All those fruits are in the carousel system. Finally, to reach a sufficient caloric amount for the astronaut, we added the root system to grow potatoes. Potatoes gives a huge amount of calories and grow well in such a system. The aeroponic team had to find how to grow them in the best condition as possible. Letitia and Nancy were in charge of finding the best lamps and nutrients for the growth, and Thomas and Francois were doing an optimization work by making scheduling to know when and what kind of vegetables we had to plant next in order to always reach our daily intake goal.
Once upon a time, an astronaut called Bob was on a space station, and he wanted to eat vegetables. But how could he grow them easily? For any vegetables such as tomatoes, broccoli, eggplant, cucumber, carrots, etc., to look like this, and finally be able to eat them as Bob wants, during their growth, vegetables need to have access to the right amounts and types of light, water, and nutrients. LED lights are used to replace the sunlight and to allow plant growth. Moreover, a nutrient solution is sprayed on the plant roots until the vegetables are nutritionally interesting enough. The magic potion contains the essential nutrients to grow vegetables, such as nitrogen, phosphorus, and potassium. And finally, Bob must take into account all the parameters that could influence the veggie's growth and thus be able to eat his salad and be happy forever.
In order to grow plants in outer space, a GrowbotHub team designed a specific module. This module uses an aeroponic system to monitor the plant's growth. An aeroponic system consists in holding the plant by its rod, leaving its roots hanging in the air. Then, at a regular interval, a solution containing the nutrients needed to grow the plant is sprayed on its roots. This solution is stored on the bottom of the module to be reused later on the next spraying interval. This solution is constantly monitored by using some sensors in order to be sure that the nutrients level are adequate for the growth of the plants. Here you can see a video showing how the module was designed. It was carefully designed in order to hold every sensor and everything at the right place at any time. A pump is also used in order to reuse the water that is stored in the bottom of the tank.
Okay, so Leah presented us a lot about vegetables, aeroponics, and how to use them in space. We've also seen how to which type of nutrients and which type of light we need to use for these vegetables. And also, really briefly, they presented the scheduling algorithm that we use to know when the vegetables are ready and when they need to be moved from one system to another one. But actually, we cannot only rely on stored data, and we also want to observe how the vegetables are behaving. And for that, we use machine learning and computer vision to study the vegetables.
Imagine a smart garden that knows everything about the fruits and vegetables growing, where they are, how well they're growing, their health, and if they're ready or not to be harvested. That's what we try to do with artificial intelligence and what we call computer vision algorithm. Using cameras placed on top of them, they're continuously monitored. We can detect the place of the vegetable. We can also know which type of vegetable it is, and also know its stage of growth. And finally, the computer can tell us when a vegetable is ready to be harvested.
We've seen how to study the vegetables and know if they're at the right stage of growth or what is happening to them, if they get sick or whatever. Now we've seen that we have a lot of different complex parts in the system and we need something to link it all together. It's what we call our top-level controller.
Private controller is the control room of the system. It is the part that controls everything and makes sure that everything works together to achieve our goal. So there is different parts to the top private controller that can be kind of separated. Firstly, there is all the part that is controlling the aeroponic system with the control of the pumps, of the different captures and sensors that are used to record data. There are also cameras that are running to get some vision. It also controls the scheduling of the light, when the vegetables should be exposed to light, when they should be exposed to dark. Different kinds of vegetables need different amount of nutrients in order to optimize the growth. So in order to reproduce this effect, we're using different shelves with different amount of nutrients in each of them. The scheduling algorithm is used to move the different vegetables in the appropriate shelves at their appropriate stage of growth. In order to correct and optimize even more this scheduling algorithm, we're using some vision with different cameras in order to obtain visual data that we can exploit using machine learning to know with certitude the stage of growth of the vegetables.
Okay, so we've seen everything that links the different parts of the system, and now there is one part remaining on the carousel system. It's the robotic harvesting.
So, when the top-level controller decides that a plant has fully grown, it instructs the robot to take the plant and put it out in the bin here. Or when there is a plant that has to change from one site to another site, it also instructs the robot to simply change the carousel, take a new plant, rechange the carousel and put the new plant in the new bin. The top-level controller is using the ROS network to give instruction directly to the controller of the robot that's interpreting the command and moving the robot.
I just wanted to say a few words about the different parts that we can see on the system that have been 3D printed. As you may know, we can use lunar soil to do additive manufacturing. That's why all the parts, like the part holders, we decided to 3D print them, as it would be a lot of kind of useless stuff to bring into space. We also worked a lot with fingers that are attached to the gripper. For example, for the potatoes harvesting, we are working with flexible fingers, and we are still testing out different gripping solutions. Okay, now we've seen everything related to the carousel system, and now we are going to go into our new and also kind of crazy project, which is the root system to grow potatoes on the moon.
Hello everyone, my name is Martin and I'm a master student at EPFL in mechanical engineering. I was in charge of developing the root system, the second system produced by GrowbotHub. As you may know, potatoes are much more calorific than other common vegetables, 73 calories for 100 grams compared to 16 for salads, 16 for tomatoes, but 41 for carrots. Consequently, that is why we chose to develop the second system to provide astronauts with better food supplies. The system can be adapted, obviously, to other kinds of root vegetables, but we stayed focused on growing potatoes for this very same reason. You're wondering now, maybe, how do we grow roots using aeroponics then? So here's one of the potatoes we grow at its early stage of growth. Below the primary potato will grow a few more potatoes, up to a dozen, let's say, attached to the roots and lying completely in the dark. The upper part, on the contrary, should grow outside of the aeroponics box at artificial light provided by sunlight LED lights. Once potatoes are fully grown, the robots will be able to pick them up depending on their maturity. The problem with aeroponics, with the potato harvesting, is that it's quite challenging because you have to penetrate inside the aeroponic zone, which is wet. And unlike other kinds of vegetables where you harvest only the upper parts, which is quite easy to harvest. Now that you know how do we grow potatoes, I can show you the prototype and be more specific about it. So we are currently in my basement, as there was no place elsewhere to build the system. What I'm about to show you here is only a prototype and is not the complete root system. Due to COVID-19 situation, delays are much longer and we did not have access to university's workshop. Thus, few parts are still missing or to be shipped. But we constructed a prototype based on what we could have access to, and it is fully functional, at least for the growth period. The harvesting can only be done with both the linear rail and the robot mounted on the structure. The complete system is composed of an item structure, which shows the advantage to be really light and easily dismountable. A linear rail provided by Igloona permits the robot to move along one axis, thus allowing the robot to pick up the potatoes from different angles as they grow randomly around the roots. We did not receive the rail for the same reasons as cited earlier, and the robot is currently mounted on the carousel system. This is why the showed prototype was intended to test whether or not we could achieve a potato culture. Results show that it's working pretty well, and the harvesting was tested separately on potatoes. Later on, the robot will be mounted on the structure, and the system will therefore be completely operational. Thank you for your attention.
We've seen the mechanical design and aeroponics linked to the root system, and now we are going to go and check out how to harvest potatoes using our robotic arm.
In order to locate and detect the potatoes we want to harvest, we use RGBD camera, which is fixed here on the robotic arm with this orange 3D printed mount. So the camera has two channels. The first one is a RGB channel, so it's a color channel that we find in most cameras. And the other channel is a depth channel, so the camera uses infrared signal in order to gather depth knowledge about the environment. So the first thing we do with the camera is that we run a deep learning algorithm on the RGB data in order to locate, to detect the potatoes. And then if there are more than one potatoes that are selected, we choose one potato that is ready to be harvested. And after that, we can use the depth data to calculate the 3D coordinates and orientation of the selected potato. This is then sent to the robotic arm, and the potato can then be harvested. Let's see a demo of the robotic arm grabbing a potato. So first, the RGBD camera will send the detection, location, and orientation of the potato of one potato that is ready to be harvested. And now that the potato is detected, the robotic arm is going to be able to grip the targeted vegetable. So the first task in order to harvest the potato is to detect the potatoes that need to be grabbed. And to do so, we use a deep learning algorithm. So deep learning is a field of artificial intelligence which focus on artificial neural networks. So an artificial neural net is basically a mathematical algorithm inspired from how the human brain of the human brain function. And this is what we use here. So basically the algorithm is gonna learn what a potato is. So the first step was to take a lot of photos of growing potatoes and then to label them and to show the algorithm where there is a potato and where there are no potatoes. And then all those photos, all those data were fed into the network, and the network learned to recognize what is a potato and what is not.
I think all of the different teams had a hard time during the COVID-19, and this was also the case for the GrowbotHub project. We had a lot of students' projects that had to be cancelled because we lost access to the system and to the workshop. We lost access to the system during 12 weeks. When we were able to go back to a workshop, we were actually quite pleased because we discovered that the vegetables were still growing, the system was still working, everything was going well. There was only one thing, one of the aeroponic system that stopped working, and that was because there were no more water inside the water tank. And as we've seen with the first video, we will no longer have that problem, as our system can last for at least 6 months with the external distribution system. So during the COVID-19, we lost access to our system, and we were lucky enough that the EPFL Space Center went and gathered, dismounted and brought the system back to my place. And we have some really nice image to show about that, and I want to thank them for doing that, as we were able to continue working thanks to them. I also want to thank a lot our sponsors. First, there is KUKA, who provides us with a robotic arm, Shunk, that provided us with a gripper, Sunlight, that provided us with the lamps, the LEDs we use on both systems, ITEM, that provided us with a structure for the root system, and also Forum EPFL that is sponsoring us. I want to thank the EPFL community, the Make Fund, that helps us a lot and provide us with a really nice structure inside EPFL in order to build and design our system. The IC faculty, that was also an important help this year. And more particularly, I want to thank the EPFL Space Center that has supported us and helped us like crazy throughout the COVID-19 situation and before also. And we are really, really happy to be continuing this project with them. Thank you a lot. I also want to thank all the students that participated in the GrowbotHub and helped us realize this true prototype that we've just seen. Thank you for following that crazy idea and helping us realize it even through the COVID-19 situation. And that's all for me. Thank you a lot for your attention, and now we can go to the questions.
Thank you very much, Team GrowbotHub, for your inspiring presentation. And we have a lot of questions from the audience. Question number 1 is, what spectrum of LED do you use for the plants?
Okay, I will let Leah answer that, as she is the head of biochemistry for the project. No. It's the spectrum of the LEDs is the same as the natural light, and you can actually modify a little the wavelength that you sent, but we just received the light and we hadn't had a lot of time to have fun with them. And most importantly, run tests to know which vegetables want which type of spectrum. And also, if that was kind of linked to the question, the potatoes and the leaf vegetables don't take the same account of wavelength and time of exposure in order to produce vegetables. So we play on all of that.
I see. Thank you very much. And I have a second question. Aside from water and nutrients, are there any additives required to grow the veggies in the hydroponic system, such as pesticides or antibiotica? And would it be different between on Earth and on Moon?
Okay. I didn't get the end of the question.
Is it different between on Earth and on the Moon?
Okay, there's one thing that the vegetables need on top of water and light. It's oxygen. And as we're doing aeroponics, the roots are directly into the air, and so they have access to a lot of oxygen. And that's also why vegetables grow extremely fast, because there are more location sites. And as we are normally in a controlled environment, there is no need to use pesticides or other kind of products to remove insects or all of that, because we are supposed to be in a completely controlled environment.
Thank you very much. Thank you very much. And I have another question. Which parameters can you analyze through the computer vision regarding the state of growth?
Could you repeat the beginning of the question? Sorry.
Which parameters can you analyze through computer vision regarding the state of growth?
At the moment, we are using simply a deep learning algorithm. So as a deep learning algorithm don't need special features, it finds itself the features analyzed for the vision. We don't focus on special features, but it's like the algorithm that finds itself the features for the vision. But in the future, with also deep learning, we'll try to also, if it's, I don't know if the question is regarding technically what we're using, or more about what we can use with the algorithm. But in the future, we'll also analyze the state, the health of the vegetables and different disease.
Thank you very much. Are you thinking of making your project a commercial product to use for agriculture and earth applications?
We are thinking about earth application also, as I mentioned, with all the life cycle assessments that we are performing. I think aeroponics and hydroponics could really be a nice way to culture and grow food, but we are not sure yet if it's really sustainable. For space, it's obvious it's a really good way to grow vegetables, and on Earth, as we have a way bigger scale, we have to be sure first about the environmental impact.
I see, thank you very much. Could you tell us a bit how Igloona helps you to develop your product?
Igloona helped us because it imposes on deadlines and milestones like PDR, CDR, readiness review, and also being in contact with other teams, we can do a nice collaboration, and it's really interesting because one system like that will never fit alone. It will be part of other system, and it's a really nice way to work with other people from different countries.
So what are your next step? Is the project going to continue?
Yes, the project's going to continue next year. We'll try to improve some of the features we had this year and add some new features to the system, make it a bit more modular, and also change the carousel and have a more modular and bigger structure.
Yeah, also one thing that we didn't really talk about, but we started working on it because we are really at the beginning. We are working on space application, space adaptation, and particularly one of the most challenging thing is going to be water containment, because the plants they transpire water. There's water, you cannot lose water and have water being in contact with the rest of the system. And also even just the aeroponic system in space, in microgravity. So we just started doing simulations of water droplets in microgravity, and we are going to continue working on that for next year. Also, life cycle assessment, really, really important. Probably we'll publish something by next year. Fingers crossed.
Great, thank you. I have a related question now. You mentioned microgravity. I have a question. Does the effect of microgravity on germination, root growth, and growth direction need to be taken into account? And does your system address it now?
Microgravity is not that important, such a big deal for plants, as soon as like the roots needs to be in the dark and the leaves in the light. So we have this thanks to our pots and the foam on it that is dark and don't let the light pass. So the microgravity is not such a big deal for plant growth, as soon as they just follow the light. And yeah.
Thank you very much. How do you anticipate transport of your system to the moon? Will the design be updated to optimize for saving the space?
Of course, the design will be optimized. Like the gravity is not the same, the constraints are not the same. So the whole structure will be different. All the water distribution system also needs to be different in order to take account all the water containment and water displacement into space. So yeah, but one thing that we could bring to space is our top-level controller, because all the logic that's behind it and adjusting the values of the sensors and all the machine learning that's behind, that can easily be implemented in space. With a calibration, of course.
Thank you for the answer. Have you established a reliable water source you could use on the moon, such as recycling from waste or from ice near the lunar South Pole?
Yeah, we have PO6 and a few other teams inside Igloona who are working on water extraction. And that's also, I can go back to what I said before. It's really nice because we could use the water from PO6 and the nutrients produced by PO1 if we were into the field campaign. Yeah.
Thank you very much. You mentioned in your system you're growing potatoes. So how do you imagine astronauts will cook potatoes? Will they have a stove and able to boil the water?
Actually, yeah, cooking in space is quite complicated, and that's why we chose this kind of vegetables. And actually, yeah, boiling water is hard, but the preparation of potatoes are actually simple compared to other boiled vegetables. So yeah, they will boil it and eat it. And you can also eat the full vegetable. For example, if you compare to leguminous, how do you say that? Like chickpeas, lentils, and these kind of vegetables, they produce a lot of trash, and it's a really long process before you can eat it. And that's why we're not growing this type of vegetables, but rather focusing on potatoes.
Thank you very much. And I have a related questions. Do vegetables in space taste different?
From what some astronauts told me, yes, they do, and you lose taste. That's why we grow peppers on astronauts' recommendation.
Thank you very much. Great, thank you. That was a very interesting Q&A session. And now I would like to thank the team again for their nice presentation. And thank you everyone for watching the show. Please fill in the short survey in the link below the video. And stay tuned, there is another project show this afternoon. Thank you very much, goodbye.